So I'm Thomas Park. Thank you all for staying. And I'll try to make this talk kind of amusing so that the cerveza that you had over lunch won't get you too sleepy. But today we'll be talking about open data. Europe is really on the forefront of open data, and I think this is a very exciting space to be working in. So quick introduction. I'll introduce myself and introduce open data a bit, talk about why it's exciting and why we should care about it. Then we'll look at some applications that you can use open data for, and wrap it up with some hands-on examples, so some live demos with open data. So a bit about myself. I am a software engineer from Seattle, Washington, on the west coast of the United States, and I work for Google. As Ruben mentioned, I used to work on BigQuery. I very recently switched to working in the geodata org. So basically we own, in my new role, I'm working on elements of the data that roll up into Google Maps and support features on Google Maps. How many people here have heard of or worked with BigQuery before? That's a few hands, great. So Big Data Spain has been a very good friend to BigQuery. We've been here, I think, in 4 out of the 5 editions. So last time I was here was in 2014. I'm absolutely thrilled to be back. I think Madrid is a wonderful city. Now, if there's one point that I would like all of you to take away from this talk, it is that data is money, and free and open data is everywhere. So there's one good conclusion that comes from this. Let's make some money. All right, but don't just take my word for it. This is Graham Vickery. He's a director at the OECD in Paris. He wrote in 2006, so 10 years ago, that the value of open data in Europe was 27 billion euro. I mean, this is an unfathomable amount of money for data that is free, right? So how is it that this data can be worth so much money, that it can have such tremendous value if people are just giving it away? Let's look at a couple of quick examples. One of which comes from New York. This is Ben Wellington. He's a statistician and a blogger in New York City. He was working with a data set that was released by the city of New York on parking tickets. What he found was that the parking tickets that were unpaid, that were owed by holders of diplomatic license plates, so owed by diplomats, were worth over $16 million. Now, 60 million is quite far from 27 billion, but keep in mind, this is a pretty esoteric use case, you know, like diplomatic parking tickets. So if we can hide $16 million even just in that use case, I mean, there's potential for quite a bit more value out there. Let's look at another quick example. This is David Eves. He's a Canadian journalist. He was working on a data set published by the Canadian government on charitable donations. And what he found was when he did a very simple analysis, just grouping the top earning charities in Canada by value and sorting them, he found that he had never heard of 2 of the top 3 recipients of charitable funds. When you think about it, this is really strange. If you're one of the biggest charities in a country, you would expect that people would have heard of your name. You're probably funding schools or funding hospitals or doing other types of public good. So it's very unusual that these companies were, or these organizations were entities that he had never heard the name of. The story goes kind of like this. These were fraudulent charities that were involved in a form of tax evasion or financial fraud. What would happen would be that individuals or companies could make donations to these fake charities, and then they would be eligible for a reduction in their taxes due to the fact that they were ostensibly donating to charities. The fake charity could then give that money back, withholding a percentage. Then in this case, the charity doesn't have to pay tax on its income. The person who donated the money doesn't have to pay tax on that money. So both of these parties have been able to get this money tax-free, and then the fake charities take a percentage for their trouble. So it's kind of money laundering in a way. And this costs the government of Canada $3.2 billion. So again, this is a kind of esoteric use case, you know, this type of financial fraud. But this just shows that there's a tremendous amount of value that can be unlocked even with, you know, kind of strange use cases. So this brings us to a question. What exactly is open data? And why are we seeing an explosion in the sources of open data? Why now? So the government, the city of Madrid has a very good open data webpage here. There's a link in the QR code. But they also have a pretty good definition of what open data is. So it's data published in open, regular, reusable format that's free of rights. So it has no copyright, no restrictions on what you can do with it. It's basically free for anybody to use for any purpose whatsoever. Now, there are quite a few different examples of open data out there. This is the Personal Genome Project, which is headed by Harvard University. And if you click through on this open data link here, you'll find a very well-structured data license. So they tell you exactly what you can do with it, which is anything you want, and they tell you what the restrictions are on the data, which is nothing whatsoever. So this has a very open license, which is great. That's what you want with open data. But be careful. I definitely recommend that you pay attention to the licenses in various data projects. There are things that look like open data that aren't actually open data. So this is Lending Club. They publish a very interesting data set that shows the results of loans. So whether or not the loan was repaid successfully by the borrower, or whether it went into default, whether the loan had to be collected or sent to collections. This is very cool data. You could use this to build up a model to predict whether or not a loan is going to go bad. There's actually a very excellent talk done by BigML the prior year that I was here in 2014 using this data. But be careful. I spent quite a bit of time trolling through their website, and I could not find any mention of any licensing whatsoever. So this is a data set that I'd be very hesitant to use in any kind of commercial context or any kind of production environment. So no license and no terms of service means it's not open data. So a lot of open data comes from governments and establishments like universities. So it's kind of an interesting question to think about what has caused these entities to start producing and releasing this data for free. That's taken a really core shift in worldview. You know, it costs a lot of money to maintain this data, to gather it, and to give it away. And I think there's two drivers for this, at least two drivers. One of which is that governments are often the beneficiaries of research done on open data. So as we saw with the two examples earlier with the parking tickets and the taxes, the governments directly benefited from research that people were doing on that data. I think governments also realize that open data can be a very powerful driving force for innovation in both the public and private sectors. But there's another kind of simpler explanation, and that's cost. So big data used to be truly big. It was heavy, difficult to move, took up a lot of space, and it was super expensive. So this is a hard drive, circa 1979, of 250 megabytes, and it cost about $45,000 when it was released. That's a pretty good amount of money now, but realize $45,000 at the time was basically the cost of a new house. So, I mean, this was a really stupendous amount of money. But at the time also, 250 megabytes was a huge amount of storage space. You basically wouldn't need this unless you were a university or, you know, a large research organization. So let's say that you needed something a little simpler, like 10 megabytes. This is a 10 meg hard drive from a year later that costs, this is actually a refurbished hard drive, not even a brand new one, that costs $3,500. Now, again, putting that in context, that's a reasonable amount of money now. But at the time, that was basically the cost of a new car. So the story today is pretty different. Our challenges today are not around the economics of simply paying for data storage. With cloud providers like Google Cloud Platform, storage is extremely inexpensive. So with Google, you can store a gigabyte of data for 1 month for about 1 cent. So it's, for all intents and purposes, practically free. Our challenge now is not storing the data or how we archive it. Our challenge is really figuring out how to use innovation to figure out what interesting stories exist in the data and figure out how to extract value out of those stories. So one of the challenges there is looking through this tremendous amount of data available to us and coming up with a story. This is kind of like making a good chorizo, right? If you have all of the raw ingredients, it still takes some skill and innovation to craft a good chorizo. So let's look at some applications of open data, of what people are doing with it in both commercial and non-commercial contexts. Transparency in health. This website is Air Quality Now. It measures air pollution in cities around Europe. Now, this data is coming from sensors that are in cities and regions around Europe. These certainly cost money to install, to maintain, to get the data from. But they can be very useful both for personal health, so that you can know if you have respiratory problems, for example, if it might be dangerous for you to engage in heavy exercise or something like that. But they can also guide public policy. So if you look at the geographic distribution of pollution over time, that might guide a government's policies around industry or regulations on industry or commercial type activities. Participation in community, also a very good thing that open data can help with. In the United States, for example, in many parts of the country, you do not, if you're walking your dog, you have to have your dog on a leash. But there are certain places, parks and communities, where you can walk your dog without a leash. So it's possible to scrape that information and create some interactive websites that show where you can walk your dog and let it run free and play. Then, of course, by putting that up on the internet, you can also get people to rate these areas and maybe leave comments on them. Civic improvements. This image on the right is a visualization of money gained by parking tickets associated with fire hydrants. So let me explain that really quick. In the United States, there's an almost global prohibition against parking in front of fire hydrants. Very good to know if you're ever driving in the States. It's one of the most expensive parking tickets that you can get. So this data set was put together by our friend Ben Wellington, who's obviously a big fan of parking tickets, but it's a good example of using your ingenuity, using your intuition to find interesting stories in the data. So here, the interesting story that's emerging is that the two of the top grossing fire hydrants that earned the most money in New York, between the two of them, were earning about $60,000 a year. So pretty significant sums of money. The other interesting thing here is that the two hydrants were located about 50 meters apart from each other. So that kind of raises some interesting questions, right? Why are these hydrants pulling in so much money from citizens and visitors to New York? Let's take a look at the image on Google Street View. Here's the hydrant right here, circled in red. Remember I said there's an almost global prohibition against parking in front of fire hydrants. There's a couple of exceptions. One of which is if there's a separation between the hydrant and the parking place. So here we have a bicycle path, but there's a catch. The separation has to be an actual physical separation, like a curb or a barrier of some sort, in order to have the right to park there. But the silver car here, which is obviously going to get a ticket sometime soon, has absolutely no visual indication that this is not a place where you're allowed to park. There's nothing, it looks just like a regular parking space. So this is absolutely ridiculous. You know, it's not just that these parking tickets should be so expensive and applied in this particular spot. The other fire hydrant that's a little bit down the road, exactly the same situation. But look at the date here, April 2009. This article, I'm gonna have to get another one of these. This article came out in March of 2014. So fast forward a little bit. This article got picked up by several bloggers in New York who ended up writing to the city to say, hey, you know, this is not cool, guys. If we look at October 2014, a few months later, lo and behold, the city has now painted the area clearly marked as no parking. So that's a fantastic outcome. Now, earlier I had showed a slide that said, let's make some money, but all the examples that we were looking at so far were basically around public good. So how can we actually turn this open data into cold hard cash? Let's look at some commercial examples. This is Google Translate, which I'm sure all of you know and love. I certainly do. Google Translate has the ability to translate about 50 some odd languages into each other. And I guarantee you, we do not have anybody on staff who speaks both Castellano and Chinese. All the translations are mechanically generated. One of the sources of input for the algorithms behind Google Translate is actually open data. So we can use things like documents that have been published by various European governments or minutes and motions from the United Nations, which are translated into multiple languages. So when the United Nations has a session, the transcripts of these are published in English, French, Spanish, German, so on and so forth. So we can use this as a very bureaucratic and kind of strange Rosetta Stone to translate these corpuses from one into the other. And it does a pretty good job. So here we see that El Vino Vino, the wine came, is properly translated, so it doesn't say the wine wine or the came. And it's not a perfect translation, but it does a pretty good job. Let's look at one more quick example. This is Redfin. They're an online real estate company from Seattle, from where I live. There's a saying in American English that the three most important things for buying real estate are location, location, and location. But after you've found a good location, you might want to know some other things about a property. For example, what is the property constructed of? How are the schools and the neighbors around it? In this particular situation, this is the house across the street from Jeff Bezos, the chief of Amazon. So the neighborhood is probably not the problem here, but you might have some concerns about paying almost $4 million for the house if the elementary school only gets a 3-star rating. So here, using open data, using data that's published by the county and the local governments about the schools and the construction of the houses, really enables Redfin to build a much more compelling product, a much more compelling website for their users. So they don't just have awesome pictures, they have a wealth of data about each of the properties that help you to make decisions about where you might want to live or purchase. So once we have all this open data, though, our challenge is really, how do we extract information out of it? So here's where I'd like to start talking about the product that I worked on until very recently, which is BigQuery. This is a quote from Matthias Johansson, an engineer at Spotify. He says, "Finally, I can tell the world that BigQuery is the best thing that ever happened to me." He wrote this tweet right after the collaboration between BigQuery and Spotify was published. And I have to say, you cannot pay people to write stuff like this. We probably could not have paid him enough money to actually tweet this. Yeah, people only say stuff like this when they really, truly love a product. So it begs the question, why is Matthias such a fan of BigQuery? Well, I used to work in more of a traditional data warehousing background when I worked at Amazon in my previous career. And traditional data warehousing is usually a pretty slow cycle. It takes time to load data, to generate these views. It can be a multi-day process, or multi-hour or day-long process, just to get your queries to run. So BigQuery changes that paradigm completely. For one thing, we have streaming ingestion. Now, the industry is finally starting to catch up to BigQuery in this regards, but for many years, BigQuery was one of the only big data tools that allowed you to send data to the system via RPCs and then query it immediately. So this is still something that's very nascent in the rest of the industry that BigQuery has had for many years. We also have separate billing for storage and compute. So with many data warehouses, even ones like some of our competitors' cloud services, you have to provision for the maximum of your usage. Like you buy an instance of a particular size, and it has a certain amount of storage and a certain amount of compute capacity associated with it. With BigQuery, you pay for what you use. So if you store a petabyte of data, you pay for a petabyte. If you store a gig, you pay for a gig. It's that simple. And it's really, really fast. But instead of just telling you it's fast, I'll switch to a live demo and show you. For this, we'll take a look at a data set called the GDELT project. So this is the global database of events, language, and tone. And given what's happening in the political situation in my country, I probably shouldn't talk about politics, but let's talk about politics. All right. So the GDAL database is pretty interesting. It aggregates information from books, media, newspapers around the world. We see that we have a date here, and it has actors, which will be, oops, I did not mean to put that there. Has actors, which would be like Donald Trump, for example. And then we also have information about the tone of events. So the average tone, whether it was a positive mention or a negative mention. So if we look at the details of this table, we'll see that it has almost 420 million rows, 151 gigabytes. So I thought it would be interesting to look at some of the recent Spanish prime ministers or presidentes to see how the tone of these people has evolved over time. Now, with this query, what I'm doing here is selecting each of the actors for the last 3 Spanish PMs, and looking at the tone of the articles that mention them. So what I'm doing here is multiplying the tone by the number of times that they are mentioned and the number of sources that they appear in. So this way, if Rajoy, for example, was in just one newspaper article, it would be weighted less heavily than if he was in 5 different newspaper articles about the same event. So this is a fairly non-trivial query. I mean, it's not that complex, but it's going to be scanning all 418 million rows of data. So any ideas from the audience? How long would this take if you put this into your big data system? Minutes, seconds, days? Oh man, you guys are all zonked out from Cerveza. Well, let's see how long it takes BigQuery. So this is running in a live instance of BigQuery, no magic whatsoever, and we see this takes just 4.5 seconds. So BigQuery is incredibly fast. Now this data is kind of hard to interpret though. You see we have this tabular format that has all these numbers. It's kind of hard to tell just by paging through this who the most popular Spanish presidente of the last decade was. But here's where we can start using some of the tools that are integrated into BigQuery to really get a richer understanding of the data. So I'm going to save this to Google Sheets. Click here to view. And what I'm going to do here is just put together a quick chart. So I'll format these as numbers. And I'll just insert a quick chart for this data. So I'll make it a column chart with column A as labels. And we'll rotate these slightly so that we can actually see things. 1 sec. Okay, cool. So here's our visualization. And this visualization actually kind of sucks, because what we see is, this one peak here. What's happening here, though, is that the axes have some values that are really high, so it makes it hard to see what's going on. So I'll just I'll modify this really quick, change our axes. And now we see a pretty interesting story coming out here. So we have Mr. Anzar here in the blue. And what I see is that his popularity is not too bad, but certainly he wasn't as popular as Mr. Rodriguez here. Then when we get to poor Mr. Rajoy, the story is getting kind of grim. It's not that he's being mentioned really negatively, but he definitely lacks the overwhelming popular sentiment that other Spanish PMs have. Does this kind of jive with all of your opinions? Yes, it does. Yes? Okay, great. So back to the demo here. A friend of mine asked me a little while ago, what's new in SQL? I was talking about some of the exciting things that we're developing in BigQuery, and he's like, come on, SQL hasn't changed at all recently, right? And I said, well, actually, one of the things that's really exciting is analytical functions or windowing functions. Raise your hand if you've heard of or used analytical functions in SQL. Just a few of you, okay. The rest of you, if this doesn't blow your mind, then I'm just going home. Analytical functions are a pretty interesting feature in SQL. Basically, in a nutshell, it allows you to do complex calculations. Things like Things like you could do in Excel. So for example, in Excel, let's say that you wanted to refer to other data in a spreadsheet. You could say that this cell is the average of the cell next to it and the one previously. And then you could take the cursor and zip it down the row of data, and you would get a calculation that refers to the previous data in the spreadsheet. So what if we could do that in a database? This is exactly what we get with analytical functions. So here's a quick example that comes from the BigQuery documentation page. What's going on here is that I have some data that's like a fake table, and I'm calculating a moving average, so an average over the value of the current row and the one before it. So this is kind of cool, right? We're doing a calculation of data that refers to other rows in our data set. So if I run this query here, let's zoom in on this a little bit. So what's going on here is that we have the average of 0 and nothing is 0. The average of 1 plus 0 is 5. The average of 1 plus 2 is 1.5. The average of 2 plus 3 is 2.5, so on and so forth. But wait, it gets better. We can also do things like refer to all of the values that we've calculated so far. Unbounded. Proceeding. So if we look at this here now, we have 0 plus nothing is 0, 0 plus 1 is 1, so the average of those two rows is 0.5. 0 plus 1 plus 2 is 3, the average of those three rows is 1. So this is an extremely powerful feature. Now we're referring to every single value that we've calculated so far in the query. Is that exciting? Yeah? Okay. But wait, there's more. I can also change this data a little bit. I'll explain what's going on in just a second, but I'll order by value and partition, P-R-T-I-T-I-O-N, partition by name. Okay, hopefully I did that right. So if I run this query now, I think maybe I need to partition by name before order by. All right, let's try this. Yes. So what's going on here now? I've partitioned my window by name. So I've changed my query so that I have A's and B's. If we look at the A's, it's the same. You know, the average is 0 and 0.5 as we expect. But here, when our data changes to B, we reset the window. So here we have 2 and nothing, the average is 2. 2 plus 3 is 5, so the average is 2.5, so on and so forth. So this is pretty cool. Now, why am I showing you all this? What I wanted to do for my next demo is figure out what the most dangerous intersection in Madrid is. So what is the most dangerous spot in all of Madrid? Now, unfortunately, here I'm going to have to invoke a classical, because the data that was on Madrid's website only has the neighborhood listed. So I had to turn to Barcelona to get their open data about their accidents. They actually have a data set that has the specific geocodes for the accidents. So if we look at the data here, one of the ways that we could calculate the most dangerous intersection would be basically to do an n-squared query. We can look at the distance between every single accident and every single other accident, right? Then we could take the average of those using this cool analytical function that I just showed you, and we could determine the most dangerous spot in all of Barcelona by looking at the accident that has the smallest average distance. So that means that the average distance of, say, the 100 closest accidents to that spot is very, very low. Now, I can actually do this query by computing the distance between the various geocodes using a pretty cool feature in BigQuery, which I wrote, which is user-defined functions. Now, here I have a function that will calculate the distance between a lat-long pair. It's not super complicated, but if we did this in SQL, the query would become very, very fragile. Even though BigQuery is extremely fast, this does take a couple of minutes to run. So I went ahead and generated the table already. Now we can look at this query here, which is a little complicated, but it's basically doing the calculation that we just talked about. It's doing the moving average over all of our lat-long pairs, and then ordering those and taking the 100th one down. So that will be the average of the 100 closest accidents. Now again, if we look at the data here, accidents distance, preview, details. So this is 7.185 million rows. If we run this query here, it's doing a very complex calculation with this analytical function, but it will still run very, very, very quickly. So this ran without using any cache results whatsoever in about 7 seconds. So let's look at one of these points here. What this says is that the min distance of the 100 closest accidents, the average distance of the 100 closest accidents to this lat long is about 20 meters. And if we look this up in Google Maps, we will see that this point is pretty close to the Sagrada Familia. So I can totally buy this. There's a lot of tourists coming there. This would be a pretty high traffic area. So I can totally see that this might be the most dangerous spot in all of Barcelona. But what if I wanted to get a more comprehensive view of this data? What I can do here is save this data again to Google Sheets so that I can look at it in a different tool. For this next demo, we're going to go outside of the Google platform and look at a tool called CartoDB, which is very near and dear to my heart since I work on geodata these days. What I'm going to do is just rename this file here so that I can find it later. And we'll call it Barcelona distance and load it into Carto. So CartoDB is a very powerful mapping platform. I really like the features they built into it, so I don't mind giving them some free publicity. But what I'm going to do here is load this spreadsheet that I exported into Google Drive. BCN distance. Their filtering could use a little bit of work, but we'll get there eventually. BCN distance, here we go. So I'll upload this. Take just a moment to load from Google. So one of the other cool features about Carto here is that you can connect it to a data set. So if you have data that's being refreshed on the back end, you can have this automatically update the data set. So just really quickly, let's look at this in the map view. It's kind of a mess, right? We can't really tell what the most dangerous intersection is here. Well, one of the cool features of this is that it has a SQL engine built in. So I can filter here by where min distance is less than, say, 60 meters. And if I apply this to the query, all of a sudden it's limited, it's cut down the amount of data that we have to look at here quite significantly. But this still doesn't really tell me what the most dangerous intersection is in a way that I can easily visualize. So let's go to the map wizards here, and I will turn this into a bubble graph. And what I'm going to do here is make sure that we're looking at the min distance, and I'll set it so that the small distances have a large radius, and the big distances have a small radius. So now we start to see an interesting picture emerge. The interesting picture that I'm getting here, though, is not just where the most dangerous parts of Barcelona are, but the fact that I think our data actually has some problems here. You see, we have all these spots here that are offset by, maybe 10 or 15 meters from Avenue Diagonal. So I think by looking at this, I would start to intuit like, maybe I've got a problem in my calculation here. The problem actually is in the code that I was running to generate the distances, I truncated off the decimal portion of some of the data values. So this caused all my data to shift by several meters. So using tools like this, we can gain a very rich understanding of our data and also spot problems in it. So, and as you can see, this all just took a couple of clicks, so it's very fast. It's a very powerful tool. Okay, and I think we're just about out of time. But that is all I had. So, gracias a voi. Thank you so much for having me again.